Many school classes in recent years have transitioned more and more to using electronic methods for teaching, note-taking, and work. Classes at the University of Michigan offer ways to make these methods possible, and even other universities and high schools are taking similar measures. In addition, accessibility to computing technology, including tablet and scribing devices, has increased. As possibilities for utilizing these technologies have become more prevalent and realistic, it seems that they could potentially impact the amount of waste produced in classrooms and workplaces, especially toner and paper waste, as well as energy consumption. Our group would like to explore these potential impacts and learn more about their consequences.
Here with Professor Sick, Volker Sick, and tell us about the recent transition that you've had to a paperless office.
Creating paper and printing is an energy intensive and rather polluting process. So if there's anything that can be done to reduce this, all the better. If I would be paper based in my work, I would have to carry around tons of paper every day. Or I would not be able to fill a few minutes here and there with additional work because I don't have the necessary material with me. Going paperless eliminated all that. So now I have access to all of my work files either on a laptop, even my phone. It's not only faster for me as an instructor, but also provides faster feedback to you as students.
Let's consider one sheet of letter-sized paper weighing 5 grams, printed on both sides in standard text. A few assumptions to be made in order to make the calculations possible are: first, ignore the embedded energy of equipment such as power station, mill equipment, and transport vehicles because their contribution to the net energy is small. Second, ignore the energy cost of reagents of making the paper, such as dyes, water, land area, reagents, and printing cartridges, because they are part of capital costs and are reusable over many cycles of production. First, let's calculate the energy of manufacturing pulp and paper. According to the MECS, as of 2006, the pulp and paper industry in the US used 2361 trillion BTU of energy to produce 99.5 million tons of pulp and paper products. We first convert British thermal units to kilojoules. The total process energy per unit mass is the following. For a 5-gram sheet of paper, the net energy input for manufacturing is calculated to be about 125 kilojoules per sheet. Next, let's look at the energy of transportation. Freight transportation energy cost per ton-mile for inland shipping vehicles is estimated to be 530 kilojoules per ton-mile. The energy then for transporting a 5-gram sheet from the mill to the point of sale, which is conflated here with the point of use, per mile is therefore the following. Convert 530 kilojoules per ton-mile to kilograms and divide by the mass of one sheet of paper yields 0.0027 kilojoules per mile. Let's assume the paper factory is based in Portland, Oregon, and the paper is delivered to Houston, Texas by rail. Transportation over this distance is roughly 2,300 miles. So then the transportation net energy for one sheet of paper is then the energy for transporting one sheet per mile times the total distance, which equals to 6.2 kilojoules.
Now let's calculate the energy of printing. Assume that we exclude the extra energy used in printing, such as energy consumed by the computer used to print and the production of ink. Assume the printer model is an HP LaserJet 4250 printer, which has a power rating of 0.5 amps for 110 volts while printing. And the standby printer power consumption value of this model is 20 watts. Printer power consumption while printing is then 0.55 kilowatts. Assuming the printer works for 25% of the time in a year, then the annual energy consumption for a printer is 1,336 kilowatt hours per year. Converting this number to kilojoules gives us 4.8 times 10 to the third megajoules per year. The number of sheets consumed per college student annually can be estimated to be about 10,000 sheets. Assume on average 50 students share one printer at a typical university. This gives us about 500,000 sheets per printer per year. The energy required per sheet for printing is the annual energy required per year for the printer over the paper consumed annually by each printer, which gives us 9.6 kilojoules per sheet. Finally, the sum total process energy value for the 5-gram sheet of paper in this example would be 141 kilojoules.
Unlike with printed material, usage of electronics like reading on a computer, tablet, or phone takes time and adds to the energy costs. Let's consider that the average person reads at 200 words per minute. This means the average person takes about 3 minutes to read one page or 6 minutes for 2 sides of a sheet. Energy in the form of electricity is produced and distributed at an energy cost. In this video, we will consider a thermal coal-fired power plant. Coal makes up about 13.01% of the energy source used to produce electricity. Coal-fired power plants have an average efficiency of 36% and has energy transmission losses up to 5%. Efficiency is equal to work divided by heat. The CPU and CRT display of a desktop needs up to 140 watts of power. 140 watts times 6 minutes times 60 seconds equals 50.4 kilojoules. 50.4 kilojoules divided by the power plant efficiency of 36%, then divided by the 95% for this transition loss equals to the total energy consumption of a desktop of 147.7 kilojoules. You can do the same for a laptop too. Laptops need 15 watts. Using the same method for the desktop, the total energy consumption of a laptop is 15.8 kilojoules. These values are for reading 2 sides of a sheet of paper at the reading speed of 200 words per minute. Keep in mind that these power consumption numbers are averages. Some brands and models of desktops and laptops are more energy efficient than others. In addition to the efficiency of the power plant and the power transmission losses, we must consider the energy cost of transporting coal to the plant. Assume the heat content of coal is 8,000 BTU per pound. This gives us a transportation energy addition of 500 BTU on 6 million BTU per ton of coal per mile of railroad transport of 0.003% per mile. In the case of the Monticello Thermal Power Station, this power station acquires their coal from the Powder River Basin in Wyoming, approximately 1,200 miles away by rail. 1,200 miles times 0.003% per mile equals 3.6%. This transportation energy cost adds 5.3 kilojoules for a desktop and 0.57 kilojoules for a laptop. Overall, reading 2 standard pages for the above example would consume 153.3 kilojoules for a desktop and 16.4 kilojoules for a laptop. In comparison, the energy cost of a sheet of printed paper is 101 kilojoules. Newer and more efficient technology can make desktops and laptops more power efficient, which reduces the energy required for reading electronic material. However, printed material can be reused and reread numerous times without any additional energy cost. However, this is not true for electronic materials. The energy cost for various electronic materials depends on the type. Documents which are only read over once, such as emails, require less energy cost than materials that will be read multiple times, such as textbooks and lecture notes. If it is to be reused multiple times over, it wouldn't be a bad idea to print it.